This is the first section of chapter 6, which is all about the Taylor series. Now, the first thing we're going to look at is something that you learned in core 2, which was the Maclaurin series or expansion. Okay, and what that expansion look like is this. So we can take some functions and we can write them as an infinite expansion that looks like this. So we substitute 0 into the function, then we differentiate, substitute 0 into the function, that gives us the coefficient of x. We differentiate it again, substitute in 0, divide it by 2 factorial, we get the coefficient of x squared. We differentiate it again, divide it by 3 factorial, that gives us the coefficient of x cubed, and so on. Okay, so we can do it as many times as we want. Here we're going to go all the way up to r, so that will be x to the power r, and then we can keep going like this. Okay, now we can only generate this if we have a function can be differentiated an infinite number of times. So here we just keep differentiating. You can't do that with all functions. You can with sine, you can with cos, you can with tan, you can with e to the x, you can with log of 1 plus x. All of those can be differentiated an infinite number of times. So we can only write in the Maclaurin expansion if g of x can be differentiated an infinite number of times. An infinite number of times. Okay, that's the first thing. The second thing is we are substituting in 0, aren't we, into the function itself and its derivatives, which means at no stage can I end up with 1 divided by 0. I can't have something that's not defined. So basically, with all of these derivatives here and with g itself, it must be defined at 0. In other words, if I substitute in 0, I can't end up doing 1 divided by 0. Okay, so g of x and all its derivatives must be defined at 0. In other words, if we substitute 0 in, we must get something that can be evaluated. So not 1 divided by 0, okay, or something divided by 0. Okay, we don't want that. So they're the two things that it must have. Okay, let's have a look at one of the expansions, Maclaurin expansion. Let's look at the expansion for log 1 plus x. Okay, this is in the formula book. So if we write down what this looks like, you may or may not know it off by heart, but it's x minus x squared over 2 plus x cubed over 3. Then it'll be minus x to the power 4 over 4, and so on, plus dot dot dot. So we can see that this is going to go to x to the r over r factorial, sorry, not r factorial, just r, and so on. But this expansion is only valid if the modulus of x is less than 1. Another way of saying that is that the values of x that we substitute into this expansion can only be between 1 and minus 1 for the series to converge. Yeah, any infinite series that we write, we're only really interested in ones that converge. And this is only going to converge if the modulus of x is less than 1. So I can't substitute in values of x here, or actually substitute values of x into here, into these bits here, and get any answer that makes sense if x is outside of that range. So these values that I substitute in, they've got to be in this range. Yeah. If I substitute outside of that range, the series is going to diverge and I'm not going to get an answer that makes any sense. But what happens if, say, for example, I substitute in a value that's close to one of these extremes? So let's say, for example, I substituted in x equals to 1 because I wanted to estimate or approximate log 2. So let's say I wanted to find an approximate answer to the log of 2, which means that x is 1. So in the expansion, then I'd substitute in 1 minus 1 squared over 2 plus 1 cubed over 3 and so on. Now I could work out the exact value on my calculator, but if I was to do this expansion, I would need tens of thousands of terms in the expansion just to get a small degree of accuracy. Okay, so thousands of terms needed, thousands of terms in the expansion are needed just for a low degree of accuracy, which isn't particularly useful. And in fact, the expansion for log 2 or the log of 1 plus x is better, more efficient when x is close to 0. So I don't know, log of 1.01 or the log of 0.99, things where x is small. As it gets closer to -1 or +1 for x, so getting closer to working out the log of 2 or the log of 0, it takes more and more of these terms to get a limited amount of accuracy. So Maclaurin is good, it's very clever, but there are a couple of limitations. The first limitation we've looked at: what if we have a function which is not defined at 0? How are we going to deal with that? Do we not deal with them at all? And how do we get across this problem here of having a limited amount of accuracy? Is there something we can do to improve that? And you'll be pleased to know, yes, there is a way we can overcome both of these problems, and that is actually almost by shifting the Maclaurin expansion, so it's not centered on 0 anymore, but it's centered on a different value. Yeah, this is what we call centered on 0 because we need to work out the derivatives at 0. And for the expansions, when x is close to 0, then we get good accuracy. Okay, so I'll just write that down. So I'll just put here that the expansion is centered on 0, I'll put quotes around the word centered, and the other thing is that we get better accuracy with a smaller number of terms when x is close or closer to 0. And you see that better in something like this log, the expansion of natural log 1 plus x. So as I said, the way we get across this problem is by shifting the whole expansion so it's centered on a different number, and we can choose whatever number we like, and we're going to call that a, and this creates something called the Taylor expansion or series, Taylor series. Let's do it the same way around, Taylor series expansion. Okay, so let's derive this new expansion. Well, the way we're going to do it, the first thing we're going to say is we're going to say let f of x plus a equals g of x. So g of x is the Maclaurin expansion. So what we're going to do is we're now going to write an expansion for f of x plus a. And what happens, we will end up with f of a. We had f of 0 before. So this is basically almost like a transformation that moves the whole Maclaurin expansion now that it's centered on a. Then we'll have the first derivative at a, x, plus the second derivative at a, x squared, over 2 factorial. So can you see how it looks like almost identical? It is in ways identical to the Maclaurin expansion. We go all the way up to the r derivative at a over r factorial x to the power r. So we can do this because you can almost think of the function g of x as g of x plus 0. And the 0 was what we had here. So instead of g of x plus 0, it's basically f of x plus a. So all the zeros now become a's. Now we can get a second form of this expansion by replacing the x in the first expansion with x minus a. So we're going to be replacing x in this first expansion with x minus a. Now if we do that, so basically x minus a plus a, which just becomes a, equals, and then where we have f of a, that doesn't change, and then we'll have in the next one f of a. Now the x becomes x minus a. Then we have the second derivative again at a, and then we have x minus a squared over 2 factorial. Okay, I'll do one more of those. Actually, I'll go straight to the general term. So that'll be f of the r derivative, rth derivative, if that's how you say it, x minus a to the power r over r factorial. Now both of these expansions here are called the Taylor series or the Taylor expansion. Okay, so we have two forms of the expansion, two different forms. Okay, now before we go on to which form we use and why, let's look at what we've done now. So now I've got an expansion that is now centered around a. So if I have a function that's not defined at 0, it might be defined at 2. So I'll just replace x with 2. So I basically now have an expansion centered around a different number. Yeah, so that deals with this problem. Okay. The other problem was, let's say when we were working out this log 2, because it's only defined between 1 and minus 1, working out log 2 took lots and lots of terms to get a small degree of accuracy. Well, we could move the expansion so it's not centered on 0, but centered on a different number. Let's say we might center it on 2. Then basically our range of accuracy changes. Yeah, that's what this Taylor expansion allows us to do. So which form do we use when we're doing these types of questions? So if I start with the first type, so this first type here, I would use if I want to write an expansion for a function of x plus something. So for example, if I needed to write an expansion for, let's say, tan of x, and it doesn't have to be plus, it could be minus, a would be minus. If I needed to write an expansion for this, I would use the first form. I would use the second form if I want to write an expansion which has this in the expansion. Okay, so if I need to write an expansion in terms of, let's say for example, so these are just examples here, x minus pi over 3. So I want that to appear in my expansion. I use the second form. So the first form I use when I want to write an expansion for something like this. I use the second form when I want this term to appear in the expansion. Okay, so here we're going to find the Taylor series expansion for e to the minus x, in powers of x plus 4 up to the x plus 4 cubed, all cubed term. Now, because it says it needs to be in powers of x plus 4, that needs to appear on the right hand side of the expansion, and that is the second form that we had on the previous slide. In the book they call it form B. So that is, our function can be written as an expansion, which is f of a plus f dash of a x minus a. I'll just write out the next one, because once you've got the next one, you know the pattern. So the second derivative at a, and then x minus a squared over 2 factorial, and so on. So our function is e to the minus x, and we need to choose a suitable value of a, and in this case a is going to be -4, because the expansion is x minus a, and you can think of x plus 4 as x minus -4. That's the same as x plus 4. Yeah, and since the expansion needs to be x minus a needs to be -4. Right, so we've got our function, which is e to the minus x. So we need to work out the value of that function at a, which is -4. So that will give me e to the 4. Now, just like Maclaurin, you need to differentiate and work out its value. Here at -4, with Maclaurin it would have been working out its value at 0. So I differentiate, I get negative e to the minus x. Its value at -4 will be minus e to the 4. Then I differentiate again. That will give me e to the minus x. So the same as the first term. I work out the second derivative, its value at 4, because now this expansion is centered on -4 rather than 4. And that will give me e to the 4, same as the first term. And I differentiate the last time, because this will be what is going to be the coefficient of the x plus 4 all cubed term. So I don't need to go any further. And this is minus e to the minus x. And then this value. Now you can do 3 dashes, or you can put the number 3 here to show that you're finding that third derivative. Whatever you prefer. You may get confused when you're doing lots of dashes, but I'll stick with the dashes. And its value at -4 is going to be minus e to the 4. So now I can plug all of these values in to the expansion. So e to the minus x is equal to f of a, which is e to the 4, plus the first derivative at 4. Now that's actually minus e to the 4 x minus a. Now remember, x minus a is 4, so it's x plus 4. Plus, now we'll tidy this all up in a minute, it's going to be the second derivative at a, which is e to the 4. That's over 2 factorial, and then times by x plus 4 all squared. Then the next term is going to be the third derivative at -4, which is minus e to the 4 over 3 factorial. over 3 factorial and then x plus 4 all cubed. Right, so we'll write out our nice, neat, simplified answer here. So you've got e to the 4. And I'm guessing what we could do, we could factorize out the e to the 4 at the end. We'll have a look. Then the next term will be minus e to the 4 x plus 4. Now don't expand out the brackets, yeah, because the question says we need to leave it in powers of x plus 4. So we don't expand the brackets. Then the next one, well, if we're going to be dividing by 2 factorial, that's basically the same as dividing by 2. So we've got a half e to the power 4 x plus 4 all squared, and then the last term, this is going to be a negative, so minus e to the 4 over 3 factorial. Now 3 factorial is 6, so you get 1/6 e to the power 4, and that's going to be times by x plus 4 all cubed plus dot dot dot. So we can factorize this. You can take e to the 4 out, so you'll have 1 minus x plus 4 plus half x plus 4 all squared minus a 6 x plus 4 all cubed. So here we have our expansion, which is centered around 4. Okay, so notice that this question is different to the last one in that we need to express tan of pi over 4 in terms of powers of x up to the x cubed term. So it's almost like the question's like the other way round. And this is where we use the first form of Taylor's series, Taylor's expansion, where we want to write an expansion for f of x plus a, which will be f of a plus f dash of a x plus f double dash of a over 2 factorial x squared and so on. Okay, so if our f of x equals tan x, then f of x plus a is going to be tan of x plus pi over 4. So that means that a equals pi over 4. Now we could have just written that down. A equals pi over 4 straight away. So just like before, so if we want f of x equals tan x, I know I've got that already, but I just want it all to match up. So I can now work out f of a. So that's going to be f of pi over 4. So tan of pi over 4, like tan of 45, is 1. Then we'll differentiate. This is in the formula book. Tan differentiated is sec squared. So sec squared x. So I now need to work out f dash of pi over 4. So that will be, sec is like 1 over cos squared. So cos squared pi over 4. So that's going to be 1 over the cos of pi over 4 squared. So that becomes basically 1 over root 2 all squared, or 1 over a half, so that becomes 2. Then we differentiate a second time. So we use the chain rule. So the first thing we're going to do is to write sec squared like this. So if we use the chain rule to find it, then that will give us 2 sec x basically to the power 1, if you use the chain rule there. Then multiplied by sec differentiated. Now sec, again, that's also in the formula book, and sec differentiated will give you sec tan. So we're just using the chain rule there. Sec x tan x. Okay, so we'll tidy that up. So we'll actually have the second derivative as 2 sec squared x tan x. We need to work out f of, or f double dash of pi over 4. Now we don't even need to use our calculators at this point because we already worked this out. Okay, this part here was from our previous part 2. And we also worked out what tan x is. We worked that out in the first one. That's 1. So basically it's just 2 times 1 times 1. Yeah, so look out for things like that. Don't think, right, I've got to grab my calculator and work it out. We just got to use what we did before. So that's 4. Okay. And then we're going to differentiate a third time. Now when we differentiate a third time, we're going to think of what we had before and use the product rule again. There are things that we can use from before to help us. So if we call this part u and this part v, when we differentiate it, so we're going to have u 2 sec squared x times by v dash, that's tan differentiated. Well, we've got that already, sec squared. So that's u v dash plus v dash, or sorry, v, which is this tan x, times by u differentiated. Now u differentiated, we did that in the previous part. Sec squared differentiated becomes what we got in the previous section. So it's going to be times by 2 lots of what we had last time, which was 2 sec squared x tan x. Now we don't need to actually simplify this, because actually in this form it actually makes things easier. Yeah, because we work this out. Sec squared x we know is 2. Okay, sec squared x again, so we know that this is 2. Tan x we worked out, well, we know that tan x is 1. I suppose I should do that in green really, if we're going to make everything match up. Okay, that's 1. And this bit at the end here, let's do this in blue. The 2 sec squared x tan x was what we worked out in the last part. That was 4. So all we need to do, if we're going to work out f triple dash of pi over 4, all we need to do is multiply them together. So we're going to have 2 times 2 times 2 plus 1 times 2 times 4, which gives us 16. So keep referring back to the previous bits that you've done, particularly on questions like this, so that you're not working out things from scratch again. Yeah, that does help. Right, so now we're ready to write tan of x plus pi over 4 is equal to this expansion. So f of a, which was f of pi over 4, which was 1, plus the first derivative, which was 2, so we've got 2x at a. Then the third derivative, sorry, the second derivative, that gave us 4. So we basically get 4 over 2 factorial, which is 2. So 4 divided by 2 is 2. So you get 2x squared. Then we get the third derivative at a, which is 16. So we're going to have 16 over 3 factorial, which is 16 over 6, which is 8 over 3. So then plus 8 over 3 x cubed. And then we can just put plus dot 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 here. Okay, so there's our expansion for tan of pi over 4, or tan of x plus pi over 4. Okay, show that the Taylor series about pi over 6 for sine x in ascending powers of x minus pi over 6 up to and including the term, so we only need to go up to this squared term, is given by this expression here. So here, because we want x minus a to appear in the expansion, this is where we use the first form of the Taylor series or the Taylor expansion. So we'll have f of x, the function can be written as f of a plus f dash of a times by x minus a plus f double dash of a x minus a all squared over 2 factorial and so on. Okay, but we don't need to go any further than that in the question. Right, so I guess the first thing that we need to do is to write down what's the value of a. Now in this case, a will just be pi over 6. It's not going to be like negative pi over 6 or anything like that. And our f of x is going to be sine x. So then f of a, f of pi over 6, which I think is sort of sine 30, isn't it? This sine 30. So probably one that we would probably know off by heart. But yeah, sine 30 is going to be a half. Or sine pi over 6. Let's differentiate. Sine becomes cos x. So we now want cos of pi over 6. And if we do cos of pi over 6, we get root 3 over 2. We differentiate again, so this one's a nice easy one to differentiate. We get minus sine, and we don't need to go any further because we're only going up to the x squared term. And then f of pi over 6 is basically going to be minus a half, minus what we got from the first one. So now we can write out the Taylor series or Taylor expansion. So sine x is equal to f of a, which is going to be a half, plus f dash of a, which is root 3 over 2 times by x minus a, and a is pi over 6, plus, we only need to go as far as this. Now this is actually going to be minus a half, so let's just put minus a half here. It's all going to be tidied up in a minute. Divided by 2 factorial. Okay, so maybe I will write it like this. So plus minus a half here over 2 factorial x minus pi over 6 all squared. Now I've left it like that because I need to show that it gives a certain expression anyway, so I'm going to have to simplify it. So half plus root 3 over 2 x minus a, so that's fine, that doesn't change. Then negative a half divided by 2 factorial, which is basically like negative a half divided by 2, which is going to be negative a quarter, and then x minus pi over 6 squared. So I suppose I should be writing that this expansion goes on, but it looks like we've got what I asked for, so we've proved it as required. So we go on to part B. Part B says, using the series in part A, find in terms of pi an approximation for sine 40. Now this is pretty straightforward because basically all we're going to do is we're going to substitute x for whatever the angle is. So basically substitute x for 40, but we are in radians, so we need to change 40 to radians, 40 degrees to radians. Now if we do that, so 180 is pi, so or 360 divided by 9 is going to give you 40 degrees, that's like 2 pi divided by 9, isn't it? So I could have 2 pi over 9. So remember, we're working in radians. So that's all we need to do, is just substitute. So sine 40, now remember, we haven't got an infinite number of terms. So sine 40 is going to be an approximation. So we shouldn't really write equals. So it's going to be half plus root 3 over 2. And then 2 pi over 9 minus pi over 6. I'm just substituting it into my expansion. Minus a quarter. 2 pi over 9 minus pi over 6 squared. Okay, so what I'm going to do, now I can write equals, is work this out on my calculator. Let's see what we get. Now I said use my calculator, but I didn't read the question. In terms of pi, so I shouldn't really use my calculator. So I've got a half plus root 3 over 2. Now 2 pi over 9 minus pi over 6 is pi over 18. And then minus a quarter. Then I'm going to have pi over 18 all squared. Right, so let's see what we get. We get a half plus, that will be pi root 3 over 36 minus, now I don't know what 18 squared is, that's 324, and that's going to get times by 4, so 1296, so minus pi squared over 1296 plus ... So we can't really simplify that or factorize it. So that will be our answer in terms of pi. What it might be interesting to do, I'm not going to do it, but what you could do is actually compare that answer to what the actual answer for the sine of 40 degrees is, or sine of 2 pi over 9. And actually I think I will do it. So let's have a look. So I work that out as the exact answer. So this is sort of just extra work here. I said I wasn't going to do it, but never mind, I'll do it anyway. So the exact answer, sine 2 pi over 9, sine 40, from my calculator comes up as, I'll write down everything I've got, 0.6427876097, and the approximation I get using what I got down here, I get that approximately 0.6433453115. Okay, well, they agree to 3 dp, don't they? Agree to 3 decimal places. Yeah, so they both give us 0.643. Do they? No, they agree to 2 decimal places. Sorry, I need to work on my rounding. They both agree to 2 decimal places, so they both give 0.64, which isn't bad, I suppose. We only use 3 terms, and I'm guessing the more terms we used, the better accuracy we would get. And actually, the closer the angle we choose to pi over 6, the even better accuracy we get. We chose 40 degrees. This is centered about 30 degrees, isn't it? So maybe if we shifted it a bit, we could get even better accuracy, but that's not bad. 3 terms, and we've got accuracy to 2 decimal places. Okay, you should now be able to do exercise 6A on pages 134 to 135. Just a quick recap of the 2 forms of the Taylor series. And here they are. I've not mentioned this before, but neither of these are in the formula book, so they're not in the formula book, so they need to be memorized. Okay, but the Maclaurin expansion, the Maclaurin series, is in the formula book, and if you've got that, I think it's quite easy to use that to help you to write down these two Taylor series, and they have slightly different uses. The first use is if we want to write an expansion of f of x plus or minus something. So I'll write an example of that. So e.g. if I wanted to write an expansion of, let's say, e to the x minus 5, I would use the first form. Whereas in the second form, if I wanted to write an expansion in powers of x minus 5, then I would use the second form.